Trying to get students and teachers to think about mathematics as systems of relationships. So these are relationships between problems. So using a problem you know to solve a new problem, or using concepts that you know, prior knowledge to gain insight into new problems, or try to grapple with different representations, sort of aligning and mapping together different problem solutions, or different manipulatives. So the idea of this is that mathematics is not necessarily, many students, teachers, people engage with mathematics as sort of, a set of procedures to be learned, but rather we can think about it as this more systematic set of relationships. This builds, you may notice, on things that Nicole McNeil was speaking about last week. So it actually is a really nice sort of next step, I think. So for example, let me show you what I mean by mathematics as relationships. Every equation, this is what we talked about last week, can be thought of as a set of relationships, right? So relationships between left side and the right side. And here you have a little bit more complex relationship, but still, what's happening on one side of the equal sign, equivalent to what's happening on the other side. And the insight that students need to gain is that these are all the same kinds of relationships, right? So there are these higher order relationships between, some kinds of representations and the relations within them, and these larger sort of understandings and these higher order relationships. Now, this isn't just the case in equations. So, for example, when people are engaging with manipulatives, what you want to know is that, the reason teachers use manipulatives is that they expect students to gain the understanding that these manipulatives aren't important in their own right, but what's important is the relationship. So here, the relationship between different manipulatives is the same as the relationship represented in that symbolic notation, as well as in this graphical representation. So here the perceptual features of these three representations look very different. They aren't automatically, clear why these are similar, but the underlying relational representation here is the same. You also want students to be able to do contrast, right? To understand that even though these actually look very similar, they are in fact different, right? They're representing a different relationship that's underpinning there. So I sometimes think about this more broadly in work that I'm doing with Susan and a number of you students as well. I think about higher order thinking a little more broadly. And so when we're talking about higher order thinking in mathematics, you can think about it as this process of looking at relationships between relationships, right? That could be between, representations like manipulatives. It can also be between problems. So here, these are two different problems. One's a permutation, one's a combination problem. They are different sort of categories of problems, but yet, if you understand one, you can use that knowledge to understand the other, or to draw insights. We can also make comparisons between multiple solution strategies. And this is something I'm going to follow up with in more of my talk. This notion of comparing multiple representations, in particular solution strategies, is something that educational recommendations are increasingly highlighting. We should have conversations where students talk about their different ways of solving, and we want to highlight that there are multiple ways to solve problems, and comparing misconceptions to correct solutions. But what that means is that you have to be doing these kinds of higher order comparisons between them, right, in order to actually be gaining something from these comparisons. And I just want to highlight that this isn't, I think, this notion of comparing relational representations isn't something that's really specific only to mathematics. You can think about science. Systems thinking is increasingly, something that we're thinking about in science. So rather than trying to teach science as a bunch of different pieces of information to understand, we don't want people to look at this and say, students to engage with this as it's a volcano, this is lava, but rather to understand, what the system of relationships is here, right? So we're, increasingly trying to think about more systematic sort of relational information as something that's important for students. So this idea of seeing these relationships. Higher order thinking in the 21st century, I just wanted to throw this in there because we have Bloom, who came from the University of Chicago, and developed Bloom's taxonomy, which probably many of you are familiar with. It was definitely something that when I was in my Learn How to Teach TA class in graduate school, they introduced, Bloom's taxonomy as something we should be thinking about in making sure that your class is doing something beyond teaching students to memorize information and regurgitate that back to you. But Bloom, in a edition of his book after the original one, he described his taxonomy as the most cited and least read document of all time. It's one of these things that everyone sort of has taken their own ideas about and then run with them, right? We all know that we want students to gain something more than just regurgitating, but what exactly does that mean? And actually the taxonomy was originally designed as an assessment tool, right? So to help assessment designers to develop assessments that are able to capture more of these knowledge pieces, but that's different than thinking about the design piece. Sort of this Bruner idea of going beyond the information given. What exactly does that mean? Well, my own personal way of thinking about that, the way that I frame a lot of this work is about thinking about these as relationships and sort of drawing students' attention to this idea of envisioning the world as these sort of complex systems of relationships. I think that's a really rich way to engage. We know that students aren't really coming out of our current mathematics program all the time with this orientation. This comes from a set of questions that were given to community college students as part of a study that Karen Given and Jim Stigler designed. And these community college students are students who have graduated from high school. They have decided to continue with their education. These are not students who are totally disengaged with school and these orientations, but their ways of thinking about mathematics are not what we might hope. So for example, here, they asked them to solve these problems. I'll give you 2 seconds. You've probably been looking at this while I was up here anyway. You think about how you were solving it. Basically, what they found out was that students solved each of these problems separately. So 10 times 3, and then 10 times 13, they write out the thing. 20 times 13, they write out the whole formula again. And so rather than looking at these as relationships, 77% of them calculated these answers separately. So they're not sort of orienting toward mathematical problems as something where you might be able to gain from one to understand the next, right? How about things like place value and these kinds of procedures? They sort of ask students about why you would put a 0. In this case, one of the students says, I don't really know. I don't know why it's done like that, but it's the way I was taught to do it. I just did it like that. I don't really know the answer to that, though. And so, this sort of orientation that that's beyond. Why would I need to know that? This is just how I do it, right? Equivalency, how could you check your answer? Students were very comfortable saying, I could subtract the 50 or 715, I could subtract 253. They say, could you subtract 462? And they said, many of the students were not sure. They said, and went through that, discovered that in fact you could. This is something that basically the students were not these students were not organizing around these notions of mathematics as sort of these representations that could be thought of as really relational ways, right? Okay, and then this was in direct contrast to the community college faculty who said things like, I went into math specifically because I didn't have to memorize anything. And I realized my quote didn't show up here from this one, but it said something like, that's just how math is, you just memorize it, right? So it's these sort of direct opposite ways of orienting. This is something that's been changing. Common Core standards have increasingly drawn attention to the role of mathematical thinking and reasoning, in particular through their standards for mathematical practice. So things like putting into the standards that we need students to be good at problem solving, reasoning abstractly and quantitatively, doing pattern recognition, making use of structure, right? So using a lot of these sorts of tools and sort of ways of thinking about mathematics that go beyond just, sort of focusing on these curriculum standards as separable, isolated content pieces. But it's a struggle, right? Teachers often struggle with how to do it. curriculum designers, have to think through what does that actually mean in terms of the design of these sorts of activities. One of the modes that has been getting a lot of attention has been the idea of mathematical discussions. So bringing students to the table, right, and having, sort of group conversations, small group or large group conversations about problems. So rather than the teacher starting the lesson and what is the typical US model, usually there's some kind of a warm up to the lesson. Then the teacher says, today we're doing a lesson on something or other. They might give a example of how to solve a problem, and then, the students try out that solution, right? So an alternative way was to give a sort of interesting problem, then have the students try to solve this problem, and then come back and have a discussion about the different ways that students solve these problems. The typical way to do that might involve, calling on different students. And then the question is, what do you do with those solutions that the students have generated? What do you do with one that's wrong? What do you do with one that, is right in this particular situation, but it might not be right always, right? There are a lot of complicated decisions that teachers have to make as they're going through that kind of a conversation. And so many teachers say, it's a lot simpler to not have that conversation in a very rich way. So you might kind of entertain the conversation a little bit, have people say some, how they solved it, but just, sort of verbally call on some people, but not really make that a very, sort of rich part of the conversation. So I want to think about how we can make mathematical discussions more powerful, what makes them hard, what makes them effective. And if you think about mathematical discussions, if you're comparing solution strategies as being a set of a moment for actually doing this kind of relational comparison, then we can develop some ideas, sort of building on the work that we know about how relational reasoning work. There's this long line of basic cognitive research on reasoning, and so maybe we can take some insights from that and improve this sort of everyday important context of mathematical discussions. All right, so what makes relational reasoning hard? It's a big literature here. There are sort of a few things. Two of the main ones are knowledge. So you have to have enough background knowledge in order to engage with a relational reasoning opportunity. So some of this work comes from developmental work where if children have no knowledge or insight into a particular set of words or something, it's very hard to do an analogy about them, right? So you need some prior knowledge. There's also a piece of this which has to do with the ability to hold and manipulate these representations in mind in order to actually see the relationships between these different representations. And so I and others have argued that executive function may be a really important piece here. And I'll just say what I mean by executive function, since I know we're a bit of a diverse audience. But within that, I'm including both inhibitory control and working memory. So if you take this problem, do this for a second. Suppose 5 days after the day before yesterday is Friday. What day of the week is tomorrow? So it's sort of maddening, right? Okay, so what that is showing you, you're trying to manipulate this in your working memory. You're trying to hold, the relevant parts of the problem in mind while you're, doing one step of the problem, and and that's interfering then with doing the next, kind of step, right? So this is an example of how you would need working memory. In mathematics, it's the same sort of a representational problem. So there are two parts here. You're trying to hold this all in working memory. You're also trying to sort of inhibit the piece that you don't need right now, right? And sort of what's the other piece. So these are the two components of working memory that I'm really going to highlight. They come out the strongest in children as well. Adults also see more of set shifting. We can talk about that later if you're interested. Okay, so in a classroom, if we take these two ideas, so we need knowledge and we need working memory and executive function resources, teachers need to engage students in opportunities for drawing comparison that build on their existing knowledge, make relational correspondences salient, so they don't overtax the available attentional control and working memory, right? So we want to see if there's a way to provide kind of support so that you're not overtaxing these working memory resources, and by helping to draw attention to particular, what is particularly important in making these comparisons, we might provide less taxing on the inhibitory control, sort of what's irrelevant, what's relevant. Okay, so in this talk, I'm going to show some evidence that pedagogical practices to support relational reasoning actually can improve students' mathematical thinking and learning, demonstrate that this kind of learning is cognitively demanding, and showing that individual differences in executive function predict gains from learning in this sort of a way. Providing evidence that we need to think about executive function when we're designing instruction to make sure everyone's learning. I want to talk a bit about a different way that executive function resources might be reduced in a learning context, such as pressure from identity threat based in stereotypes. So we had Claude Steele here a few weeks ago, which again, this is like really nice leading up to this talk, but he gave the really interesting and important lecture about the role of stereotypes and how this sort of threat of a stereotype can lead to reduction in performance on measures, on tests, and part of the literature that's come out of that has argued that part of the reason for that is that it's a tax on working memory and executive function. And so if we know that executive function is important from learning from something like a complex relational comparison moment, then a tax on those resources may reduce learning. So we'll talk about that. I won't have time for it, but I have some other interesting research about the role of math anxiety here. So if anyone's interested, you can ask me at the end. Okay. We know that having students make connections actually has some relationship to larger achievement differences. So sort of earlier work has found that was looking at teaching practices around the world that was looking for things that were common across high achieving countries and lower in lower achieving countries like the United States and Australia, which was the other piece of this particular study. And this project looked at lots of different information about the countries and about teaching in these different countries. So for example, looking at the class sizes, looking at teacher credentials and prior learning experiences, looking at kind of hours in school, all of these different things, looking at teacher-centered instruction, student-centered instruction. None of those things were reliably common across the high-achieving countries and not common in the low-achieving countries, except for, so the only thing that came out as common in this way was looking at how teachers actually had students draw connections between problems and larger concepts. So basically they did a code that said whether or not a problem that was given in these lessons, all the problems that were given, whether or not it had an opportunities for drawing connections. It was sort of a rich problem. And then the second code for whether or not the teacher actually enacted the teaching in a way that required students to make these connections. And in that second code, the US used those kinds of problems as frequently as in other countries, but when you look at the actual enactment of the way that they taught those things, there were like almost 0% of the time that these teachers taught these lessons in ways that the students actually had to generate these relationships and these connections. Whereas in Australia, they did that a little more often, and in the higher achieving countries, they did it much more often. So these data are a little old, right? So hopefully we've changed since then. But this is something that we're struggling with, that I think we struggle with in terms of thinking about how to actually make students engage with relationships that are happening, that are available sort of within the problems and within the concepts in their lesson. Okay, and then I did a study looking at particularly comparisons that these teachers use. So when they actually sort of made some kind of an explicit comparison between problems, between solution strategies, between representations, and again, basically you see the same number of comparisons across these different, so I looked at just Hong Kong, Japan, and Hong Kong, Japan, and the United States, and basically we found, this was 30 videotaped lessons, Hong Kong, US, and Japan, 520 comparisons. And basically, we find that in all of the different ways that we looked, the teachers made these comparisons as often, but they provided less kinds of support to ensure that students actually gained from these comparisons much less often. So things like making these, if you're comparing two things, making them visually presented, making the source visible while you're talking about the target. So if you're saying, oh, one kid made this misconception and the other kid solved it this other way. Let's think about how those are, similar or different. Why do you think they're different? So they did this orally much more often than making both of them visible at the same time. If they were visible, whether they were spatially aligned, it was again more common, these other regions, whether they used gesture that actually moved between these different representations was less common in the United States, whether they used a source that was familiar. So we said that prior knowledge might be an important piece of this in terms of making relational thinking easier. They were less likely to use the familiar source and to use imagery as well. All right, so you see kind of across the board, these teachers may be less likely to actually require students to be making, relationships and making these connections, and they're maybe providing these kinds of interactional supports less often. All right, so all of this is correlational so far, right? So we're looking at just frequencies of these patterns. The next question is, does this really matter as far as learning if you can, if you vary them experimentally, right? Okay, so, let's just move that, okay. All right, so many of the studies that I do in my lab, and many of the people are here that work on them, involve an experimental paradigm where we're trying to get as close to everyday practice as we can while maintaining experimental control. So what we'll do is we design a lesson that is sort of allowing for these, higher order thinking, these kind of comparison opportunities, and then we, work with a teacher to make sure it's a really good lesson, and then we videotape that teacher teaching this lesson with real students, and so, but we videotape it with a bunch of cameras at once. So what that allows for is us to then post that lesson. We edit these videos, and we can create then experimental stimuli that have the exact same audio stream, the exact same sort of craziness that happens in real everyday classrooms, but we've had kids picking noses, falling asleep in class, all this kind of stuff. But we therefore have two lessons that are identical except for some particular things. So we can, manipulate some of these kinds of support practices that I was describing and see whether they're actually going to make a difference. We then administer these new videos to new classrooms of kids, and there we can randomize within classroom. So each student is working at their own computer, and they're doing these interactive lessons. So if they're working with a computer, they're not in an actual classroom, but they're engaging with these, lessons which have real kids and real classrooms, and sort of teachers teaching, in instructional ways. A lot of the content that I've been using for these videos are centered on ratio. I don't know if you can read these. I can't even read them. Anyway, they're very funny. Basically, they begin with very little understanding of what ratio means. So I don't know. I guess it's something that's in your car. I don't know. It's sort of like a race or a skin color. I know that ratio is a noun. So I think the definition of ratio is a pasta made in India. Yes. Oh, shoot. Oh, weird. On my computer, it looks normal. Huh. Okay, let's see. It's swapped. So on my screen, it's just the regular.
If you go up to the top, you can swap display.
Swap displays. Do I have to go to the menu or wait?
Go back to where your slides are showing. There's a thing at the top. See it above that says swap.
Oh, it's just on yours.
You have to look up there.
Do you see my cursor? I don't see
I only
it.
know this because it's happened to me in public.
Huh. Yeah, it's so funny. I've never had this happen.
Oh, it's swapped.
Can you see my cursor anywhere? Because my cursor's on here. My cursor is moving here. Oh, there we go. Okay, wait, which is that one? Aha, thank you. You saved me. Okay, very good. All right, excellent. Okay, so, they're coming there, something for math, okay? There we got math, at least, right, in our solution. Okay, so these kids start with very little understanding of ratio. So, for this study, so you can see what this looks like, we compared whether or not it mattered. So those first two on those support lists, whether it matters that you have a source visually available, or visually represented, and whether it's visually available at the same time as the thing it's being compared to. So we created 3 versions of the same exact lesson where either the video was edited so no solutions were on the board, so the teacher just said, how'd you solve it? How'd you solve it? And then so the student watching the lesson just hears it. The all visible was where you actually saw the solutions written on the board. And in the sequential video, you saw the solution that was being described, being written on the board. So you got the source visible, but you couldn't see it again. So after they finished describing that solution, they would talk about the next one. And that's actually something that we see, very often in the US lessons, at least, at the time of the previous video, where basically, the teachers would very often either just do it verbally, or they would maybe put up one, and then they would, they say, well, that's a misconception, they take it away, and then they put up the next one, and they say, so here, this is actually how you want to solve it, right? So sort of one at a time kind of a solution. Okay, so, and then the post-test measures had 3 constructs, so looking at procedural understanding, looking at flexibility of sort of how to know when to use a particular solution and how to use it in different, slightly different contexts, and conceptual understanding, so understanding how and why, things like being able to define ratio and give some explanation. And basically what you find is that if you compare the all visible and the not at all visible, having these as visual representations is helpful. Not entirely surprising, I think, but something that's worth thinking about, right? So in developing these mathematical discussions, maybe it's really important to make these representations visible. But having them visible one at a time was actually not that effective. And what we think happened was that what this meant was that the way this was organized is first we did a misconception. And we think that the students, some of the students really, memorized that first one. And if they weren't actually then given the support to see the relationship with the subsequent solutions, didn't, even though they saw 1 incorrect and then 2 correct solutions after that, didn't necessarily see the relationships between them, and thus really just memorized that first one. So the working memory load maybe was too much to sort of really draw that those comparisons and build a larger understanding. Okay, so we hypothesized that this was a matter of sort of reducing this executive function demand, right? So having these richer representations, having the actual visual representation. So why was this worse than not having any visual representations? Well, maybe having this rich, really nice, source that was this misconception was a very rich representation, which then it was even more demanding to sort of say, oh no, wait, but that's not right. I need to, actually take in this other one. So if we go back to this idea, all right, maybe we want to build in some experience, some familiarity with the prior, so this prior knowledge piece with the problem and the representation itself. And also, maybe we want to be trying, also to reduce this executive function. So in a second study, we used a new video. So these are new teacher, new students. This is with 218 fifth grade students. So again, we could do random assignment within classrooms to these videos. And here we did 2 things. So one was we did the same thing, so trying to see whether we replicated this visual representations versus, visible representations versus sequential instruction. And secondly, we did a familiarization with division in the context of the problem that we were going to be using prior to the lesson so this was a worked example with division or an unrelated warm-up kind of a problem. So very often teachers will do some kind of a warm-up at the beginning of the lesson, but so you either had one that really was sort of like made a familiarization or one that didn't, right? And so here, and this is work, by the way, that, so Emily did a lot of this, design of the warm-up and everything, and many of you were part of this. We find that when you look at the misconception, so here, if you look at the misconception, having this prior worked example versus the unrelated warm-up didn't seem to make too much of a difference. But having the reduced executive function lesson, so again, we sort of replicated that having this, visible representations seem to make a difference in reducing people's use of the misconception. So this is changed from pretest to the delayed. And then when you look at the, when you look at the correct solutions, we again see that reducing the executive function demand in these lessons was important. We also see, though, that this combination of having this prior worked example with division actually led to an even greater gain for students in that, who got this reduced executive function lesson, right? So it suggests that maybe together, these kinds of, if you have a lesson that's really allowing students to fully engage in the content, not be overwhelmed, having this kind of a prior knowledge piece might allow them to, benefit even more from the lesson. Okay, and these are kind of, new data we're sort of trying to think about. Okay. Now, let's see, for some reason this is going to go back to that. Okay, so in a different study, we were looking at trying to see whether this difference, whether the sequential, like the low performance in the sequential study, and this was actually done before this last one, so we didn't try to keep hitting kids on, with the lesson that we thought would be ineffective. We actually thought they would be effective, but because it was pretty standard practice. But here we used administered individual difference measures of executive function to try to see whether there were going to be differences in who would gain from these lessons. Because the thing that's actually important to think about is that not all students are missing the comparisons that are happening in these lessons. Some students are really gaining from them, right? Some students are, it doesn't matter whether it's a low EF or high EF demand lesson. And so the question is, is that the case? Are there certain protective factors maybe, or particular ways that people are going to differ in learning from a particular lesson? I won't go into the details of the executive function measures, but basically what we see is that inhibitory control did predict learning from this lesson. So this one that was, so this was the lesson where you saw sort of low, if you just on average, lower performance, lower learning, but it really seemed to separate by by the executive function resources, here inhibitory control resources of the individual. So if you have higher resources, you see pretty good learning. If you have lower resources, you see lower learning, and we see the same thing for working memory. So basically, what we see is actually these executive function skills didn't predict where you started that much. It was a little bit here in procedural, but mostly we don't see differences in where you start. Rather, we're really seeing differences in learning from a particular lesson. So this may provide some kind of an explanation for relationships that are well documented between executive function resources and math achievement. So we know that kids with these higher resources tend to have higher math achievement scores, but we don't really know why. Maybe that's because they're actually learning more from these kinds of lessons that aren't really well supported. So if we really well support our lessons, can we get all kids to learn just as much? Yeah.
So, that was just my question. For the well-supported lessons, do you narrow the learning gap?
Yeah, you do.
Groups?
Yep. So we did the same thing, and I didn't report it here because it's not that fun to look at, but you don't see any differences for the we didn't find differences here, systematic differences for the highly supported lesson. So
it doesn't hurt anybody, but it helps the kids with lower executive.
Right, these particular lessons, that's exactly right. So that's what we see. And so that's, so the message here is not that, some kids are going to learn more, but rather we want to think about how to redesign lessons in order to ensure that students are not, systematically learning less, right? Okay, so basically, this suggests that even with the same instruction, controlling for pretest knowledge, children may gain differently in procedural flexibility and conceptual understanding based on these sort of executive function resources. And this is all within the typically developing range. So ideally what we want to do is to change practice in order in sort of these details of instruction to ensure that students are gaining more, sort of more equally from these lessons. All right, so how about differences in executive function that aren't maybe what you come in with, but maybe they're about, that are sort of layered in by the demands of the context itself. So things that are more like situational cognitive load. Does adding a context demand load executive function and decrease learning by analogy? And you know what, I'm realizing that on all of this, well, anyway, I hope that my students' names they were supposed to be showing up here. So anyway, hopefully they'll come up, but because you guys have worked on these projects. But basically, what we know is that, there are a lot of reasons to know and believe that people are often encountering pressures, identity pressures within classroom contexts. So Margaret Bill Spencer has talked about sort of PVEST model. She was the one who first talked to me, sort of gave me this framework for thinking about lessons. And, I said, well, people have all these different executive function resources. And she said, well, there are a lot of different things that load your resources and your sort of demand during a learning context. And I said, well, that's a really good point. I need to think more about that. And Jackie Eccles has also done a lot of work showing that people, sort of have identity pressures in classroom contexts on a regular basis. And so you heard last week from the man himself about stereotype threat. So, just to, show you the figure, so one of these studies, for example, showed that when told that a particular learning or a particular test could identify gender differences between people, you saw men outperform women, but when they were not told that there was a gender difference, you didn't see, this gender difference. So this suggests, and this, and other work is really suggestive of the fact that that there is something that when you feel under the potential threat of a stereotype, learning and performance may go down. And most of this work has always been about performance, but not about learning. And other work done here by Sian Bylock and colleagues, Susan Levine as well, have shown that you see the strongest effect of these stereotype threats for high working memory or difficult content. So on a test that has low working memory demand, you might not see these effects show up, but on items that require sort of more working memory demand, you see it in a more serious way, which suggests that there may be something about the working memory load that gets imposed by these situational contexts. That's really what's the mechanism of sort of why you see these stereotype effects. And you tend to see the strongest effects for highly identified, high working memory participants as well. So people who maybe, you might think that having a larger working memory would be protective, but at least what they found in other studies is that the largest working memory participants may be those who actually show these largest effects. So if you have this potential for state cognitive load, is relational reasoning likely to be impaired by stereotype threat, right? So if we know that relational reasoning requires executive function, okay, there might be. So how about a gender threat? So one of the first studies we did here was looking at a gender threat with undergraduate women. This was, we looked at learning, so whether or not stereotype threat has the potential to impact learning from these kinds of a context. So for this study, we used a videotaped lesson, which was a comparison between permutations and combinations, so that you saw a figure from it at the beginning. This is again, it's sort of an opportunity for comparison, but it requires working memory to align and map these different representations together. And we gave them an instruction at the beginning that said, this lesson and the following tests have been shown to display gender differences in the past, exhibiting lower scores for women than men. So again, not a anything about you in particular are likely to do poorly on this, but sort of invoking this potential for identity, judgments of performance. And basically that's what we see. So in both at an immediate and at a delayed test, we see that these women who had received that first, gender threat tended to be learning less. So the fact that we see it over a delay also suggests that it's not that they still are feeling that sort of immediate pressure, but that really they, retained and really took in this information differently. So again, it's suggesting that these kinds of, online opportunities, not online like computer, but like within your everyday context, sorts of pressures, these reminders of identity may be actually impacting learning itself, not just test performance. And this is important because test performance, which is where most of the stereotype threat studies look at, it's very important. Your test performance has a lot of impact on, where you're going in future trajectory. But at the end of the day, you have that knowledge, right? So you're still likely to be successful in what you're doing. So if your learning isn't getting impaired in the first place, then you may have also these sort of large systemic implications, right, for your knowledge building. That's beyond my work right now, but it's just something I think to think about 'cause it's potentially important. Okay, so then how about younger children? Do we see this kind of relational learning impacted by stereotype threat? And is high executive function protective, or does that make you more susceptible? So here, in this stereotype threat paradigm, we see this was with 135 fifth grade students, and this is part of Emily's dissertation, so you may hear her talk about it later. And we looked at particularly the students that were involved in this study were in schools where there were minority race or ethnicity participants, mostly African American and Latino participants. And they were told before the lesson, so it was the same videotape lesson that we saw before, researchers at the University of Chicago are conducting an important study of how students like you learn math. Please answer the questions on page 1 of your packet now. And we asked them then to rate their race. So we didn't say anything negative about race or ethnicity. We didn't say anything about their, the sort of performance on these measures. It was merely an identity sort of reminder. And we used a measure of executive function that was called the D2. I can talk about that if you like. And basically what we see is that if you look at the learning, you see learning that as expected, as expected, the high EF did better on this, learned more from this lesson than the low EF participants. But when you look at the participants who were in the stereotype threat condition, you see that there was a decrease in learning that was present at the immediate, but numerically, but not significantly. But then at the delay, you see sort of a serious difference in the information that was retained, and the problem solving at that post-test. And what's also particularly interesting is that, important, is that Emily also included measures that were beyond just the content of these items. So she also asked about enjoyment. So how much did you enjoy that lesson? How much would you like to learn more about this? At the end of the packet, there were some optional math puzzles, and we said, if you'd like to, solve some, you can solve some of these problems. And basically you see that the children who were in the stereotype threat condition did all of these less. So they had impact in sort of the way that they were engaging in mathematics, potentially beyond, just the content acquisition itself. So this suggests that not only is threat of stereotype potentially seeming to impair knowledge representations, but also may have longer term impacts on interest and engagement. So this is, we're just starting to get some insight here, but it's giving some, perspective on the fact that you can have these sort of situational context factors that are loading, resources, but then having sort of larger impacts on the way that kids are engaging in classroom learning. We have performance pressure data, which are much more confusing. So if we want to talk about them in the discussion, I'd be happy to. And this is work, by what Emily and Almaz is also working on. So what I'd like to sort of pull together is that we see the individual differences in executive function can predict classroom learning by analogy. So this suggests that there seems to be, this is a rich way to design classroom lessons, having comparisons is a rich way to design classroom lessons. However, we need to be sensitive to the fact that children's executive function varies, and this is something that, could be a mechanism explaining broader relationships between executive function and achievement, and this may be something that we can really then, if we understand this, we can actually change and manipulate the way that we're enacting classroom lessons to reduce executive function load. And ways that we've done that so far seem to be making a difference. Yeah.
Is there any evidence that in the countries that do use the better supported math lessons, students with lower and higher EF don't suffer as much in math performance? Because that would be what you would think.
Right.
That EF makes a
that there's sort of a smaller range.
In the US,
right.
Where the lessons tend to be not supported, but less of a difference, like in Hong Kong and countries that do, give the support.
Right.
Lessons.
Yeah. No, that's a great point. I have to think about how you do that.
A lot of reviews say it's very closely related to math achievement, but maybe that's because of the way you teach it.
Right. Yeah, absolutely. No, it's a really interesting. I mean, right. That's the idea, right? That's what I was thinking. But it's an interesting question to start looking at the range in EF. Yeah. I mean, there is some reason too. It's a little bit hard to compare because executive function measures seem, performance sometimes changes by country. I mean, so.
Unless PISA measured it or something.
Right. I know. I don't think they have. I mean, because you guys used skill as a proxy for working memory, right? Which, is maybe related again, but not necessarily the same. Yeah.
But I think they I was at a meeting where, you were there too, where that PISA guy talked about putting these kinds of measures into the...
Right, I know. I mean, if they do, I think that would be great. If they did, I mean, they were going to do like the non-cognitive, right? So I don't know whether EF goes in there because it's non-cognitive. I don't know. Yeah, no, but I agree. I think that's a really interesting one. Yeah.
In terms of supporting the learning by analogy with the verbal part of it, are the teachers actually saying what the relationships are, or are they having the students self-generate the analogy?
They are, so the way that they do both. So we're trying to, the way that they're actually taking these lessons, they don't just sit and watch this videotape lesson, they answer questions. So the teacher in the real classroom says, which of these do you like better? Which one, and we'll start to ask, like, how are these similar? And then the video pauses, and the students watching it have to usually they write on a piece of, they have a packet. So they're actually having to do work in generating, because what I'm guessing is your intuition is that I think that's really crucial, right? So I think that's what's really the main driver here, is actually making sure that the student actually engages in that way. Just having the teacher say it is not likely to do it. Yeah. Yeah. Yeah.
Lindsey, how will teachers eventually learn about this kind of research, or this research?
Yeah, I mean, it's a great question. I mean, in our work, what I didn't talk about today, one of the things that we do is we interview teachers, not always, but we have different, sort of different ways that we've done this, but we try to interview teachers whose classrooms we're using, and that way we provide this information. We also get information from them, sort of their, we don't sit in the classroom every day, right? So we're trying to understand their intuitions and expectations and about whether these are going to be effective practices or not. But our hope is that way we can also tailor our dissemination to them in ways that are actually engaging with what they're thinking about. So one of the things is, we have found that our teachers are really attuned to the idea that these practices may differ in their efficacy for different kids. So cognitive scientists, we tend to like to say, like, you need to do X, but the teachers would say, well, wait, that'll work for my high students, but not my struggling students. They're not talking about executive function. They're thinking about, and so we've been trying to understand a little better, what are they thinking about when they say that? Do they mean prior knowledge? Do they mean, behavior management? Do they mean executive function? Are they sort of getting that? And so one of the sort of messages that we've gotten is that, we really need to make sure that our recommendations are sort of, tailored to thinking about student differences and how to best support, all students in the classroom. But yeah, so right now we're doing these sort of smaller, kinds of dissemination practices, but I'd love to think about how to, have broader conversations. Yeah, so I'll just summarize and then we can, talk. So stereotype threat here seems to reduce learning and engagement with high demand mathematics instruction, and we see that, these sort of temporary reductions in executive function could explain, we're seeing it in very small scale, right? But if you extrapolate, could potentially explain persistence in achievement gaps, particularly among high EF youth who, are sort of the, have the potential to be the really highest, achieving in these classroom contexts, and potentially, if they're, kind of having enough of these moments, then you may have sort of these larger term experiences and sort of, maintaining achievement gaps even as we improve the quality of the classroom lessons themselves as far as the content. Okay, and I'll end there and maybe we can have some discussion.